Hi everyone, welcome to part 4 for our video lecture for section 12.3 on the calculus in polar coordinates. In our previous video lecture, we went over how to figure out the area that is bounded by a polar curve. In this video, we're going to be extending that concept to the area that's bounded by two polar curves. So I want to begin with this example. Example 6 here is asking us to find the area of a region that is common to the two regions bounded by r equals to -6 cosine theta and r equals to 2 minus 2 cosine theta. Now notice that this example here is pretty much the same thing as example 2, or at least the two same curves. But in example 2, I was only asking you guys to figure out the points of intersection. In this example though, now we want to figure out what is the area that is bounded by those two curves. So let's take a look. Now as usual, we begin by making a sketch, but since we already had a sketch from the previous example, I'm just going to go ahead and attach it here. There we go. And for this one here, I'm still marking what were the angles that were giving us the points of intersection. And remember, we said that one of the angles was 2 pi over 3, the other one was 4 pi over 3 in the bottom, and we were also having an intersection at the pole. So, what is the region that is bounded by these two curves? Alrighty, so it seems like this region right here is the one that we're trying to figure out the area for. So how do we do it? What do we do next? Well, remember that in order to figure out the area, we need to define some bounds. What are going to be the angles in which we're going to be finding the area? So I'm going to give you guys a big hint. Anytime that you're working on these problems, always draw some lines going through the points of intersection and the pole. So I'm going to draw one line here. This one here is theta equals to 2 pi over 3. And the other line going through the second point of intersection and the pole is going to begin here by theta is equals to 4 pi over 3. Now, how does that help us? Well, it is helping us because notice that for the region that we're focusing on, we have areas that are given by the cardioid and we have areas that are given by the circle. So notice here, for example, the area that is given by the cardioid is the one that is right over here. All of this region is given by, or is the area that's inside the cardioid, but notice here that you do have some pieces on the outside, this one's right here, that are not being given by the cardioid at all, but instead they are the areas that are inside the circle. So we need to make a distinction there. All right, now, before we proceed though, I do want to simplify my work a little bit, or maybe a little, maybe a lot. So notice here that this region here happens to be symmetric across the x-axis. So rather than focusing on multiple regions to find out, like this one, this one, this one, and this one, if we recognize the symmetry, we cut down our work in half. Okay, so I'm going to get rid of what we're not going to be needing. So I'll ignore the axis of symmetry here. We already recognized it. Get rid of this region, this region, this region, and since we're not going to be using anything on the bottom half, I'll get rid of this other line. Alright, so now we just need to focus on basically two regions. Region 1, given here by the area that's inside the cardioid, and region 2, which is inside the circle. Okay, so I'm going to treat these regions separately and evaluate them or figure out the areas individually. So let's go ahead and begin with, well, this one here was area 1. I'll put here region 1, call this one here region 2. Alright, so let's go ahead and focus on the area for region 2. There we go, here is my brief little sketch here. It doesn't have to be perfect, but what I do want to know here is what are the angles that I need to go and sweep this area. Now we know that we have one of the angles is 2 pi over 3, but what about this one right here? To answer this question, we could go ahead and use our graphing calculator. Now, as you're using the graphing calculator, always begin by looking where the angle theta equal to 0 is located at. And there we go. That's a hint. Where is theta equal to 0? So going to our graphing calculator. Alright, so making sure that we have our functions. Yeah, we have -6 cosine theta, that's the circle, and 2 minus 2 cosine theta, that's the cardioid. Alright, so a couple of things that we can do here. We can either take a look at the graph and click here on trace, and select 0 for theta, and see where it is. Alright, so it looks like when theta is equal to 0, I am given the position on the circle, not the cardioid. So how do we figure out the position of the cardioid? Well, we can just go here to our curve and, well, to the graphs here, get rid of the circle, click here on graph, only the cardioid, and repeat the same step. And let's see. Okay, well, it seems like the position of the cardioid corresponding to theta is equal to 0, it is at the pole. Now, if it is at the pole, and if we know that the full cardioid is being traced when the angle goes from 0 to 2 pi, well, it makes sense to say that if I wanted to reach the halfway point, then the angle theta here, it's most likely pi. We can always verify it. If I change my window setting and go to theta max, not going to 2 pi, but instead just going to pi, click on graph, there we go. We are tracing half of the cardioid. So perfect. Now we know what are going to be the values for theta that will be giving us this area right over here. So we can go ahead and set up our integral. We can say here that the area is going to be given by the cardioid as it goes from the angle 2 pi over 3 to pi. So we're going to put here 1/2 times the integral from 2 pi over 3 to pi for r squared, so a 2 minus 2 cosine theta squared d theta. So there we go. This is the area for, oops, I call it R2. This is the area for region 1. I guess the naming convention doesn't matter, but I did call it R1 here. All right, so now we know this area. Now I'll let you guys work on this integral. I'm just going to go ahead and give you the value that I got. So for this one here, I get approximately a 7.039. Okay, now is this the only region of interest? No, because we also had R2. Now, what was special about R2 here was that, well, the area for R2, it does not involve the cardioid at all. This one here is the region that is trapped by the circle. So I'm going to go ahead and make a separate sketch here for R2. And there we go. Here we have our R2 region. And once more, we want to figure out, okay, well, what are going to be the angles that we need? Well, we already know that one of them is the 2 pi over 3. But what about the other angle? So in this case, we want to figure out, okay, well, what is the angle here? Oops. There we go. Put this, what is going to be this angle? Because we want to know, yeah, as the angle varies here, between here and here, we want to figure out what is the area that is being given by the circle. Now, this one here is actually two different ways of doing it. One of them is to figure out, okay, well, you know actually that the circle is intersecting at the pole here. So what you could do here is say, okay, if it's intersecting at the pole, I can set the equation r equals to -6 cosine theta equal to 0. And this one here is going to give you cosine theta is equals to 0, which tells you then that theta is equals to pi over 2. And again, we knew that because, well, the circle was actually crossing the pole right here. Now, that's one way of doing it. If you wanted to, you could have also used a calculator. So I have here highlighted the circle, so graph it. Okay, we get the full circle. But I will give you a warning though. I never changed my window settings, and my window settings are still going from 0 to pi. So in this case, in polar, we're actually tracing a circle when theta is going from 0 to pi. So if I went to the trace here and figure out, okay, well, when the angle is equal to 0, notice here, like, okay, you're at the -6, but to do the full circle, you only need to go all the way to pi. So it must mean that halfway through is pi over 2. And we can verify it here, trace pi over 2. And there we go. We are at the desired location. Okay, so it seems here then to figure out or to get the area that's bounded here, all I would need to do here is set up the integral. Well, 1/2 times the integral as theta goes from pi over 2 to 2 pi over 3. For the radius, which is given by the function, -6 cosine theta squared d theta. And again, I'm going to go ahead and just give out the answer. For this one here, I get approximately 0.15. Now, are we done? Not yet, because we've only figured out what is the area on the upper half. But what about the bottom half? Well, we just need to essentially multiply our results by 2. So I'll put here the total area is going to be equals to 2 times R1 plus R2, which gave me approximately a 15.708. And there we go. All right, so now as you can see here, these problems can be a little bit trickier because we always need to be mindful of what angles we're using to calculate an area. Now, before we go over another problem, I want to give you guys another animation. So here we have our circle, and if we focus only on the angles going from pi over 2 to 2 pi over 3 here, notice what happens here. As I increase my number of wedges, then I indeed get the desired area that we wanted. Now, if we do the cardioid, which I'll do here. So here's my cardioid, but for this one, we were focusing to get the area. We were going on from the angles from 2 pi over 3, so I'll put it here, and the angle pi here. All right, so there we go. That was the area that we were focusing on. And as we increase our number of wedges, there we go. That's the area that we got. All right, perfect. So now let's take a look here at another example. Okay, so for this problem, we want to find the area of the region inside the rows given by r equals to 6 times, oops, this should have been a 2 theta. And so r equals to 6 sine of 2 theta, and inside the circle given by r equals to 3. Alrighty, so as usual, we begin by making a sketch, or in this case, I'll use my calculator and just attach it. But let's see here, how do our graphs look like? Well, let's see, we have y equals 2, we have the circle, r equals to 3, and our rows, which I'll put in red here, and this one here was 6 sine of 2 theta. So taking a look here, whoops, now remember, we have to change our window, so just click zoom fit. There we go. So now we have our roses our rose petals and a circle. Perfect. Now for this one here, since we're only being asked to find out the area of a region inside one of the roses, we don't need to use all of them. So I guess I would focus only on the one on the first quadrant. All right, so we know that 4 roses are being traced as theta goes from 0 to 2 pi. So if I wanted only 1 rose, then I only need 1/4 or 1/4 of the interval. So 1/4 of 2 pi or 2 pi divided by 4 should be pi over 2. So I'm just going to go ahead and change my window here from 0 to pi over 2. There we go. And let's see, graph, there we go. That's only one of the roses. Now for this one here, I'm going to go window or zoom, fit. There we go. So that's what I'm going to be working on right now. I'm going to go ahead and attach this image in OneNote. But before I do though, I will make my rows a little bit smoother. So I'm going to change the step here. So the step, I'm just going to say, let's go for pi over 100. There we go. Smoother curve. All right, perfect. There we go. All right, so what do we do next? Well, remember, we always need to figure out the points of intersection. In the other problem, we didn't find them because we already knew them. But for this one, we don't know. So we want to figure out, okay, well, where are these graphs crossing here, here, and we also get to look that, well, we just have 2 points of intersection. So we don't need to worry about like other ones where they might be intersecting at the pole. No, this one's here. They're going to be a little bit more straightforward. So I'm going to set my equation here. The rows was 6 sine of 2 theta. And this one here is equals to the circle, which I'll put this one here in blue. All right, so what do we have then? Well, it seems like we have here that we're looking for the solution where sine of 2 theta is equals to 1/2. Now, what is the angle whose sine value gives you 1/2? Well, we're going to have a couple ones. The sine value of pi over 6 gives you 1/2, as well as the sine value of 5 pi over 6. So what this tells us then is that the angle here, 2 theta, must be equals to pi over 6, and 2 theta must be equals to 5 pi over 6 as well, which is going to give us our 2 intersections. We're going to have here theta is going to be equals to pi over 12, and our other intersection here is going to be located at theta equals to 5 pi over 12. Okay, in fact, I'm going to put this one here in green because the next step is, once you figure out your points of intersection, you do want to graph a line going through your points of intersection. So we're going to have one line here. This one here should be the theta equals to pi over 12. And the other one here should be the theta equals to 5 pi over 6. Now, let's see. What else do we need? Well, we pretty much have everything we need. We are somewhat ready to set up our integrals now. However, I want to note here that this problem is asking us to find the region inside the rows. So not just one petal, it is actually asking us to figure out the region that's inside all of the petals and the circle. So I'm going to go back to my drawing, well, my graph here, and change the window so that I'm actually including all of the petals. So going from 0 to, 2 pi. There we go. Graph it and change zoom to zoom fit. Okay, so we're going to be looking for all of this area. However, since we have symmetry, we just need to find the area that's trapped between the circle and one petal, and then just multiply that area by 4. Okay, so let's go ahead and take a look here. So what is our region of interest? Well, it looks like our region of interest is all of this, but this here could be separated into different regions. I'm going to call this one here region 1. I'm going to call this one here region 2, and this last one here region 3. So let's see. Let's focus first on region 1. Now for this one, if I just make a brief little sketch here of region 1. So there we go. Here's my region 1. And it looks like the area for region 1 is the area that is being swept here as we go from one theta value all the way to pi over 12. But what is our theta value here? Well, again, guys, ask yourself, where is the value associated for theta equal to 0? Because we want to know where our graphs start. So where is theta 0? Now, more specifically, where is theta 0 for the rows? Because notice here, region 1 is not being affected by the circle at all. So where is the theta value for 0 on R1, which is given by the rows function? So I'm going to our calculator. I'm going to go window. I'm going to go ahead and ignore the circle. And focusing only on the rows, I'm going to go here, click trace, 0. Okay, so it looks like theta 0 corresponds to the pole. So really then, it looks like we're going from the pole, put here theta equal to 0, and then going all the way till pi over 12. So for R1, the area is going to be given by 1/2 times the integral, as our angle is being spanned from 0 to pi over 12. And the r here is our rows function, which is a 6 sine of 2 theta squared d theta. Okay, now again, I'll let you guys practice this integral, but for this one here, I get approximately 0.408. Okay, now what about the area for region 2? And again, for R2, I'll make a quick little sketch here. Okay, now for R2, we get to see here that, okay, well, this time around, the area is being found by essentially the circle, and it's the area that's being spanned as theta goes from pi over 12 to 5 pi over 12. So this one here was a little bit easier. Area 2 here was equals to 1/2 times the integral as theta goes from pi over 12 to 5 pi over 12 for the radius squared d theta. Okay, so this one here gave me approximately a 4.712. Okay, now what about R3? So let's take a look here at R3. I'm going to go ahead and make another sketch. There we go. And once more, we get to see here that for R3, the circle is not involved at all. We're just only focusing on the area that is being given by the rows here. Now it's given by the rows as theta goes from pi over 12 all the way to what angle? So what is the angle theta that takes us from 5 pi over 12 back to essentially the pole? So what is this angle? Well, since we know that essentially one of the roses or one of the petals is being formed as theta goes from 0 to pi over 2, then this one here is pi over 2. So to set up our integral, then we're going to have here the area for region 3 is the integral from 5 pi over 12 to pi over 2, well, 1/2 times the integral of our r being given by the equation for the rows, which was 6 sine of 2 theta squared d theta, which was approximately also a 0.408. Now, the truth is that we really did not have to figure out R3, because turns out here that we could have also used symmetry. R1 was the same thing as R3. Again, due to symmetry, but I still wanted to show you guys to see the importance of setting up the right angles. All right, so now that we figure out the area in 1 rows, if we wanted to figure out the total area, this one here is going to be 4 times R1 plus R2 plus R3, or I guess I could have said 2R1, but I'll put it here 2R3, and I got approximately a 22.112. And there we go. This one here is the area for, or the area for the region that's inside the rows, given by 6 sine of 2 theta and the circle r equals to 3. All right, so this is where we're going to be stopping part 4. There's still one more topic that we're missing to cover here, the arc length for polar. However, since this video series is getting a little bit long, I'll just go over that topic in class on Tuesday. Alrighty guys, have a good one. See you then.